It's 1 o'clock, so let's get started with chapter 5 of our adventure. We're going to talk today about the range of experiments that have emerged since the first successful proofs of Bell inequalities. I remember I talked last week about Bell's inequality, his demonstration, logical demonstration that quantum mechanics should predict results different than those predicted by classical physics. And he did it in a way that quickly led to experiments. In the early 70s, those experiments proved he was right. And then the whole range of questions about quantum physics and its reality were suddenly in the news. At least in the physics community, this is a topic that was only of interest to a handful of people until the first Bell experiments were successful. And here we see on this page, let me make this a little wider. Here we see some results that compare the classical physics prediction for a certain kind of experiment that involves angles, rotating angles in polarization experiments. And sure enough, the data, these circles and error bars, show that's not what happens. And in fact, quantum theory predicts the black smooth curve. And so, as I say, this opened the eyes of many in the physics community to actually conduct new experiments. And here we have the Queen celebrating with her typical wave, the royal wave function. And you see if you can figure out why that's a humorous joke. Let me alert you, by the way, to today's lecture. It has a few areas, a few sentences that are in red. Those are notes to me to make some additions to this chapter. So within about a week, you're going to see a different version, slightly different version of this chapter in the PDF archive you have access to. And I think those changes are going to help clarify some confusion that I found in reading this again. Here's Alan Aspect, one of the Nobel Prize winners in 2022 for his work. And I'll let you know something I just discovered yesterday. Aspect and one of his colleagues provide a range of courses on Coursera. Some of you may be familiar with Coursera as a teaching venue, and there's at least two, maybe more, I haven't explored everything yet, at least two classes taught by SPET that are free, and it includes quizzes and so forth. It does get technical, but if you're interested in digging deeper, this guy is the one to follow on Coursera. So you might want to consider that. So let's do some foundational discussion before we get into today's topic, and that is how light interacts with material stuff. And here's a picture I took of my house, and we're all familiar with this, but you may not have been thinking about it in the context of our class, and that is when light, whether it's in the form of waves or particles, has the feature that it is transmitted. So I was outside the house and I could see light from inside. These are the shades. but I can also see the house across the street reflected in the glass. So we're not only does light penetrate materials like glass and water and so forth, but it's also reflected. We're going to have to deal with this. Sorry, I just see a typo. We're going to have to deal with this in some of the modern experiments that exploit this property of light, its reflective and transmissive properties. In fact, we are going to see examples where very clever schemes have been developed by experimenters that allow them to choose whether light waves are superpositioned, that is, the oscillations of the wave of light is stacked. Here we have two waves whose peaks are aligned in time, and we get a large effect. But if one of those is shifted so that the minimum of this one, wave one, and the peak of wave two, if those coincide, nothing happens. They cancel each other out. We're also going to exploit this property of propagating light waves in various instruments and experiments that we're going to explore today. This is not unlike something that happens. Many of us have noise canceling headphones, where the headphone is equipped with a microphone. The microphone can hear disturbances, background noise, and so forth in the airplane you're flying in, or your car or whatever. It injects a countervailing wave, similar to wave number 2 in this version, that cancels out the exterior noise. And in an ideal case, you don't hear the exterior noise. You only hear the interior music or lecture or whatever you're listening to. So another feature of light that we will be exploiting to discuss modern experiments is what's called coherence. So you can imagine up to the point where this event occurred, the rider and the horse were coherent. That is, motions of the horse were accommodated by the rider. You've all seen expert horsemen and horsewomen. They know how to deal with the vibrations and undulations that are going on the back of the horse, so that the rider, their upper body is static, where he doesn't have those kinds of jerks and accelerations. And then we see, and that's in the quantum world, we call this coherence. And this is an example of decoherence. That, the rider has hit the ground and is sorry for it. We've also, early on, we talked about superposition of waves passing through single and double slits. And we've had the experience of, actually, I showed you a demonstration of light going through a double slit, and we saw these kinds of fringes. The blue line illustrates those. And if I covered one of the slits, we ended up with a very different shape. It has these bumps, but it doesn't have these fringes. So we've seen multiple examples of superposition of waves and how to recognize that we're looking at wave-like behavior. And again, we will see that. So this coherence I just showed with the horse and rider is illustrated here by superimposed light waves. And laser light is an example of this, where the light waves come out coherently. That is, the peaks of all the points on the output of your laser pointer or something like that are aligned. Incoherent light, like you get from a flashlight, it's more like this. Peaks are not coordinated, and you get a jumble. You do get light, but it does not have this coherent property. So let's talk about some modern experiments. We've already had multiple examples of talking about how light interacts with double slits. I just did that a minute ago, but we can also do that with physical particles, quantum particles like electrons, neutrons, protons, and even larger collections of atoms. We talked about probably two lectures ago, we talked about how large structures like buckyballs, which are collections of carbon atoms in an assembly that looks something like a soccer ball. There's 70 atoms in 60 atoms, something like that, in those kinds of microscopic objects. But even though there's a number of atoms involved, they have this property, just like electrons in this illustration, of when they encounter a double slit or other kinds of experimental shapes like this, we get an interference pattern. And that interference pattern is the same as these fringes that I illustrated here. So we've already seen, and we will continue to see, examples of how microscopic objects, not individual electrons or neutrons, but structures, atoms and so forth, exhibit this wave-like property. And here you see a history of double slit experiments. Of course, the first ones were done with light by John Young in the early 1800s. He was not doing quantum mechanics, but modern quantum mechanical experiments with double slits have evolved this way. Here's some examples of the ability of modern experiments, modern double slit experiments, to demonstrate wave-like property of particles, namely atoms. You see these big complex atoms with hundreds and hundreds of atoms in an assembly, in this case, 430 atoms collected together, behaving like a single quantum particle. And just recently, within the last 5 years, structures with 2,000 atoms. And we also have not just atomic material, but biological material, like viruses and large molecules that you might find in pharmaceuticals and so forth, behaving like waves. The electron experiments were really the first to demonstrate the wave-like properties of particles. And we see this early 1960s, electrons projected into the proper kind of experiment produce wave-like behavior. And this continues today. There are still people doing these kinds of experiments. So let me switch sharing. I'm going to go to sharing my desktop. Let's just take a second, because I want you to see this example. This is real data coming from an electron double slit experiment. And there's lots of interesting things to talk about. Each dot that appears is the result of one electron passing through the experiment by itself and striking a detector screen. And you can see over a period of time, we begin to see wave-like behavior. Now, why do I say that? Let me stop this if I can. Maybe I can't. The individual electrons are not aware of the others that have gone before or will follow that single electron. Nonetheless, you can see wave-like structure, interference fringes here and here with a darker area in between. And this experiment took, I think, a few hours. individual electrons passing through the system. So we've progressed from this scheme, which produced data. This is from in 1989. We now have these dynamic motion pictures of wave-like behavior by individual particles. And the intriguing thing is that somehow each electron knows how to behave in the double slit experiment. It knows, of course, when I say knows, the electron doesn't know anything, but it behaves by interacting with the experiment around it to produce fringe-like behavior, even though it's the only particle in the experiment at any given time. It interacts with itself, is a way to say this. And here we have another example, a modern experiment using helium atoms. Let me make this bigger so that you can see the details. And we have a source of helium collimated by this aperture, encountering a double slit, and we see fringes. And what we're seeing here is these tick marks are minutes. These numbers are minutes, which eventually become hours. And after 42 hours, again, like the electrons, helium atoms exhibit fringe behavior, indicating they're interacting with this experiment in a wave-like state. We make this a bit wider because I want to make sure you can see the details. Now, one of the key features of these kinds of experiments, excuse me, is that we can, if we choose, we can determine which way the electron, the particle or the atom, passes through the double slit. And here's an example of such a thing. Here's a source of photons, electrons, it doesn't matter, any quantum particle encountering a double slit like this will produce fringes. That's what I'm illustrating here. Now, let's suppose we change this experiment and add this little box on the back of the double slit screen. And this is designed, this is a thought experiment, this is designed to detect which slit the electron, let's just talk about electrons, which slit the electron went through. And now we're approaching a topic that was discussed by Niels Bohr. He called it complementarity. His philosophy was that you could observe quantum behavior, that is wave or particle-like behavior, but you could not detect both particle and wave-like behavior at the same time. Furthermore, he said that in order to fully understand a quantum system, you can exploit both of those views. That is, you can look for wave-like or particle-like behavior, and together they give you a full picture of the experiment. So in this case, we're seeing wave-like behavior by these electrons, but we've thought up a way to detect which way the particle has passed. And we get some very interesting results from doing this. So here's that container, that red box I showed you. And there are the two slits. We're now looking at the back of the double slit. Here's the red box. And if there are no, and this box is filled with protons, protons being positively charged. So if no electrons are in the slits, then we see the protons are in this box and distributed uniformly, and we have some electronics that tells us, is there any non-uniformity in the distribution of protons? But if an electron comes through slit one, this is slit one, we'll see a gathering of protons here because they are attracted to the negative charge of the electron. That it is the positive charge of the protons, causes them to cluster up a bit, and we will detect that. The electronics that we use in this experiment will detect, oh, the electron went through this slit. Now let's find out what that does to the fringes that I've illustrated here. It turns out if you turn on this electron detector and it's working efficiently, the fringes disappear. This is called a which way experiment. That is, if you insist on detecting the particle form of the electron with this electron detector, the system will tell you which slit the electron went through, either slit one or slit two, but you won't see fringes anymore. The wave-like behavior is destroyed. And we will continue to see this kind of behavior for the rest of this lecture as we talk about how quantum particles interact with experiments of this type. So the rule is, if we turn on our which way sensor, that is, the electron went this way or this way, we will not see fringes. Now let's change the performance, the perfect performance of this electron detector so that it is less capable of detecting the electron. Let's imagine we had a knob here so we could change the performance of this, the red box that I pointed out right here. Let's make it less efficient so it doesn't always see which electron goes through. Then we see some fringes. Faint fringes then reappear. If we turn this electron detector off completely, more or less like closing our eyes as to which way the electron went, we see the fringes as I illustrated here. So it's not an either-or thing. If we're efficient at detecting which way the electrons went, we destroy the wave-like behavior. That wave-like behavior is the only way we can see those fringes. If we make this less than perfect, we'll see a little bit of fringing faintly. More or less, what I'm saying is we would see something like the beginnings of this experiment where we just see dots randomly. So the rule is, if we probe too deeply into which way the quantum particle goes through an experiment, our attempt at seeing wave-like behavior is destroyed. So that's the purpose of this little purple box. Moreover, if we collect the data, let's imagine we don't change this from a perfect performance to 50% or 60%. Instead, let's either turn it off or on. Randomly, each electron is about to encounter the double slit, but sometimes we don't turn on this electron detector, sometimes we do. Now here's another intriguing feature captured right here. If we keep track of the status of the electron detector and tease the data we collect apart so that we have a pile of data when the electron detector was off, meaning we know nothing about which slit the electron went through, and we look at that data has fringes. If that separately, we tease apart the data where the electron detector was on so that we do know which slit the electron went through, we see no fringes. So we have two sets of data, one for the situation where we are tracking the which way of the electrons. And if we track those electrons in a separate pile of data, we won't see any fringes in that data. We're going to see this again. So the The data allows us, collecting data in experiments like this allows us to see the influence of the performance of our electron detector. Now let's make this a little more sophisticated. And this is the way this whole lecture is going to go. We're going to use basic ideas like the concept of which way detection, but we're going to make it gradually more sophisticated. So John Wheeler was a giant in several fields of physics, including quantum mechanics and cosmology and so forth. He had this idea of a delayed choice version of the double slit. And what he had in mind, it's always best to use a picture. So this is almost the same picture I just showed you, right? We have in this case, we're going to use photons. It doesn't matter. We have a light source. We have a double slit. And we have a target, a piece of paper or an electronic sensor that a piece of film or an electronic sensor that records the presence of fringes, just as we've seen many times before. But we've added to this a box that has a light sensor that looks at just this slit, and a light sensor here that looks at just this slit. These are essentially cameras. So in the way I've drawn this experiment right in this version, light encountering the two slits produces fringes, and these which way sensors, these cameras, don't see anything because this screen is opaque. But what happens if we pull that screen out? So in another version of the experiment, I take the screen, I move it to the side so it's no longer in place. And these cameras, in that case, can actually see the slits. And they can determine which slit the photon went through. And there's no fringes. Obviously, we've removed this screen that was recording the fringes. So now Wheeler's invention was, suppose we move or don't move this sensitive screen, film or an electronic sensor. Suppose we move it while the photons are in flight, where they've already encountered the double slit. And they're in the space here, the in-between this double slit screen and the film that might record fringes. But we don't make a decision about where this fringe sensor is until the photons are in this space. And we can tell when that happens. We know the speed of light. It means you have to have a very rapid mechanism for moving this or turning this sensor on. And we get the same thing I showed you before. Once the photon is in this space, it's already made its contact with the double slits. How can putting the fringe sensor in or not influence the results? Nonetheless, it does. So we make a rapid decision on a scale of nanoseconds about whether we are going to record fringes or not. And if we're not recording fringes, then we can tell these sensors back here can then see which slit the electron goes through. And based on what I've already told you, it should be no surprise. If we detect light going through one of these slits, no fringes are seen, even though the photon has already encountered the experiment. It has been emitted by this light source, traveled this distance, encountered the slits, and now is in this space. So this is why it's called a delayed choice experiment, because if you implement this experiment, you let a computer decide randomly whether you're going to be doing fringe detection or slit detection. And if you collect the data, as I described earlier, if you collect the data and keep track of whether you have this sensor in place or not, if you know which slit the photons go through, you will not see fringes. And here's more discussion of that here. So that was an early experiment conjured up by Wheeler. We have more from him coming up. Let me stop at this point and see, do we have questions?
I do not see any in the chat.
Okay. So just remember, anytime if you want to put something in the chat, go ahead and do so, because I want to make sure all your questions get answered. Now, let me mention one more thing about this. Wheeler's interpretation of this kind of experiment was unfortunately named or described with a term he liked to use, retrocausality. He imagined that the detection of the which way sensors and the fringe recording system meant that somehow nature was sending a signal about how the experiment would be configured before the photons encountered the double slit. He imagined somehow that a mysterious signal was sent to the light source so that the photons knew that they were going to be detected by a which way sensor or by this screen. The modern interpretation is no, there's no retrocausality. Each photon interacts with the screen and has its own experience, whether it becomes part of a fringe or it gets detected. And if we tease the data apart, as I described a few minutes ago, if we keep track of when this fringe sensor is in place or not, and only use the data when we're tracking which slit the photon goes through, we will not see fringes, and vice versa. So a lot of times you'll see the reference to causality or retrocausality or erasure. That's another terminology that evolved at the time. But the modern, more correct interpretation is we're simply choosing how the experiment is going to unfold. And if we keep track of the data, we'll see there's no retrocausality, does not play into this. Here's Wheeler, by the way, with he had many, many students at Princeton University, PhD students. There's Richard Feynman, Nobel Prize winner. There's Kip Thorne, Nobel Prize winner. And I was fortunate, a friend of mine got Kip Thorne's autograph recently and had Kip point it to me. So that's I wasn't delighted to get that little scrap of paper with Kip Thorne's signature. So we're well on our way to trying to understand how these various experiments could be implemented, the so-called delayed choice thought experiment, Gedanken experiment. Wheeler went further. I already mentioned that he was a leader in both quantum mechanics and in cosmology. And one of his versions of that delayed choice experiment was to propose an experiment here on Earth using light that's billions of years ago coming from a distant galaxy, in this case, a quasar, a galaxy fueled by a gigantic black hole eating up the neighborhood. Anything that comes in its vicinity would get swallowed. And if you take my course on cosmology, you'll get lots more detail about what goes on. But the light produced by a black hole of a few billion or more solar masses digesting all of the material in its neighborhood, produces a stupendous amount of output power, so much power that we can detect it here. And this light may date back 13 billion years or so into the early universe. In some cases, that light encounters a galaxy on its way to us, and the mass distribution of this intervening galaxy can lead to something called lensing. You'll see the word lensed here. And the result is here. We see multiple copies of this source. This is the faint glow here of the light from that ancient galaxy. And if you investigate this, if you look at, for example, the spectrum of the light and tease out the chemical composition of this galaxy, you'll see that same composition in these bright spots around it. You'll see the same redshift, meaning it tells us the velocity with which this galaxy is receding from us now. And so these are mirages of this galaxy. Now, Wheeler's idea was, let's use this light to perform the delayed choice double slit experiment, since we're dealing with light that's 13 billion years old. Again, this leads to his interpretation that we would see somehow the results in our experiments indicating that the early universe knew that there would be humans on Earth 13 billion years later doing experiments, and that the light produced at that time would be imbued with the properties such that when it interacted with our experiment, it would do the right thing. And again, this would be a huge form of retrocausality. That is, that the presence of the experiment and humans to conduct that experiment would cause the early universe to behave differently than it might otherwise. And so I wanted you to know these kinds of thought experiments were coming from Wheeler left and right. Okay, there's more here for you to read. Now, this is one of those sentences I mentioned. I'm going to improve this language and related artwork in a future version of this chapter. So wait a couple weeks and you'll see a different layout. But here's the idea here. A very clever experiment to further explore this double slit quantum eraser. And the eraser means, the use of that word means that people used to think by manipulating a feature of the experiment, they could retroactively cause the quantum in question to behave like a particle or a wave, and they could erase the fringes that were collected in the data. There's a new interpretation. I want you to be aware of it. And here's the clever way this kind of experiment is done. This will be updated, but this is basically correct. And here we exploit the properties of entanglement. Oh, and by the way, there's a footnote here right here to a YouTube movie. If you're interested in this, you can watch a very carefully done movie about this delayed choice quantum eraser, in which the person who created this video admits that their first version of their movie, which was made maybe 5 or 6 years ago, incorrectly embraced the idea of retrocausality, that the configuration of the experiment would somehow send a signal in the past and make sure that the quantum particle in question does the right thing and accommodates the laws of quantum mechanics. The new version that the videographer has explains that he was wrong in saying that, and the new interpretation, which I'm going to go through with you, is the correct way to think about it. So, what is the experiment? We have a light source. We have two slits. Here we have something we haven't talked about. This is a crystal. This is a so-called BBO. We'll do a little more on this kind of material in a second. When it encounters a pulse of light, it produces two photons. The photons are entangled. And modern versions of this are very efficient. Your first versions of this were not that efficient. They would occasionally produce two entangled photons when a photon of light came into the crystal. Now the new materials have been found that do this very efficiently. And the idea is that if the photon from the light source passes through this slit, it produces two photons shown as red dotted lines. One of those photons is directed into a typical double slit experiment. That is, there's some lens, there's a detector, and the detector is designed to detect fringes. So gradually, one photon at a time passes through this typical double slit experiment, the one in the green box, and we see fringes. But we also have this red signal go into this orange box, and it deals with the other red line. This red line is a photon entangled with the signal photon that goes to the fringe camera. So this is called an ancilla, and its properties tell us what the signal photon is doing because they're entangled. If we know the behavior of this, we can make a measurement of the ancilla and we know what the signal photon was doing. This box is a bit complicated. It has some detectors and prisms. We'll get into this a little bit, but there's no reason to get lost in those details. The point is, if a photon goes through this slit and enters the fringe camera, we will see fringes built up from those photons that are on this path. In addition, the other slit also encounters this crystal that creates a pair of entangled photons, the blue lines. One of those entangled pairs goes into the fringe cameras, just like the red ones do. And the other one goes into this ancilla processing box. And by using what's found at these detectors, detectors 2 through 5, we can tell what was going on with the ancilla's partner, the photons that went to the fringe camera. So now what we do is we turn on the light source one photon at a time, and we don't know which slit that photon's going to go through. That's one of the changes I'm going to make to this drawing to indicate we produce a pulse of light, but we don't know did it go through this or this slit. But whichever slit it went through, we will get a reaction in the fringe camera and we'll get a reaction in the ancilla processing center. By the way, here's the technical name of that crystal, beta barium borate. And you can buy these crystals from Amazon. They're about $100, and you can shine a light on them of the right type. You see two different output beams. So the upshot of this, we do not know which slit the original photon goes through, only that it struck the crystal. It either went through here and hit this crystal or went through here and hit this crystal. And we're feeding the fringe camera. This will collect fringes. And we're feeding this processor that tells us which slit the photon went through. So remember I said earlier, if we insist on looking very closely at a quantum process and detecting which way the photon or electron went, we destroy the fringes. This scheme avoids that. It allows fringes to be formed, and we can figure out from processing this data which slit it went through. So let's dive into what that means. So the ancilla has which way information. And this allows us to collect data that will reveal whether the electron, sorry, in this case, photon went through this slit or this slit. And we can alter this process by deciding whether we're going to use this data or not. So we have a library of data that comes out of this experiment. And for some of the data, we are not going to determine which slit was used, and that data will reveal fringes in the fringe camera. If we insist on knowing by looking in the database, what I call the library, if we insist on using the library to tell us which slit was encountered by the photon, then the fringes are destroyed. And let me show you the results of this. This was done 25 years ago, still considered a modern experiment. So here's what happens, and this is real data. If you use data from that experiment that reveals fringes, and you collect that information, you will see fringes, and these numbers are 1, 2, 3, 4 refer to the signals that are received in this processing system. So we're able to choose which part of the library we want to look at. If you look at the library in its totality, this is what the fringe sensor shows you. There's a little bit of evidence of fringes, but mostly in here where most of the photons went through, you don't see any fringes. You just see a blur of light. That's indicative of no fringes. But if you tease out from the data collected which of the ancilla were associated with photons and you don't know which path they went through, then you do see fringes. So this is what happens if you choose the data showing you which path. And this is the data you get if you don't look at which path. So you see fringes or not. And indeed, this is predicted by the laws of quantum mechanics. I want to emphasize that this result is exactly what you expect if you use the formalism of quantum mechanics and ask the mathematics, what should I see when I do this so-called delayed choice quantum eraser? It tells you that if you know the which way, you get this fuzzy blob. And if you don't know the which way, you get this. And this explanation now is the modern interpretation of experiments like this. When this experiment was first proposed and conducted, it still was influenced by Wheeler's thoughts on retrocausality. And it was called, the title of the paper involves the word eraser. Nothing's getting erased. We're just keeping track of whether the photons went through the slits and we know about it or not. And this does raise a sort of a interesting philosophical question. Suppose you run this experiment and you choose not to look at the data that reveals fringes. Just because you don't look, does that mean that you somehow confused quantum mechanics? And the answer is no. Quantum mechanics does the right thing. And if we use the data properly, it reveals that there's no erasing going on. We're just seeing two sets of data. Now, there's also a version of this Remember when I said we had a electron detector sitting behind a double slit experiment? And we could make that detector work highly efficiently and tell us which slit an electron went through. If we do that, we don't see fringes and so forth. You could do the same thing here. You could degrade the performance of this processing system, which reveals which slit the light went through. If you degrade this, all the data will show fringes. So it's not an either or thing. You have the choice as the experimenter of making the performance of this slit detection system better or worse. And if you turn it off completely, you'll see all the data will indicate fringes. So now we're into some intriguing details. By the way, some of you have let me know that you're reading books by Brian Greene, and he does discuss this issue in his book, The Fabric of the Cosmos. So if you find my explanation too detailed or too confusing, check out his book. And I think, yes, go to page 194 and you'll see a professional writer's version of what's going on here. I've given you more information, perhaps, than Greene, and I hope that has not caused confusion. So, by the way, a modern summary of this type of an experiment, the so-called delayed choice or eraser, discusses the fiction of erasure and retrocausality. We don't need those things to explain this result. Now we have a few minutes before we take a break. Now I'm going to introduce yet another technique for exploring what it is the quantum world is doing. We're going to use a scheme called an interferometer. That is, you can see where this meter usually means measurement. We're going to measure interference. We've seen interference before. Here's an illustration of it again, where we see superposition of two waves where the peaks are aligned in time and we get a big strong signal, or we see destructive interference. This is called constructive interference. It's a version of superposition. Or we could have destructive interference where the peaks are out of phase. That is, when this has a peak, this has a valley, and so forth. And that produces zero. And the interferometer lets us see this. So I'm going to spend a few minutes describing the interferometer. This is called a Mach-Zehnder interferometer, and I abbreviate this as an MZI. So if I use that terminology, don't be confused. So let's talk about forget about quantum mechanics for a second. What we have here is a beam splitter. In this case, the drawing shows a cube, and this is one of the methods of splitting light. Here's a light source produced off to the left. We can split that light into two beams using this beam splitter. It's a cube with a diagonal sheet of a partially reflecting metal film. 50% of the light goes this way, 50% goes this way. And we have two perfect mirrors, M1 and M2. So any light that comes out of the cube this direction perfectly gets reflected by this and heads to a second beam splitter. One little technical detail is we have a delay line here. I'll show you what that is. And it has in a Gedanken experiment, it has a knob. And we can change how much the wave that's going this way, we can change its position in phase relative to what's going this way by just turning that knob. We could set it like this so that the light that gets through this beam splitter is intensified for one of these detectors. Or if we turn the knob, we can produce it so that all the light goes to detector 1 We turn the knob, we can make sure that all the light goes to detector 2. And all that's happening is we're changing the phase of this wave, this one here, to either constructively or destructively interact with its partner. So here we have another beam splitter, and the light emitted by this is also 50-50, but notice it has two inputs. This beam splitter has a single input. This one has two inputs. It has this wave coming from here after going through the delay line, and it has input from the path this way, which is this. And again, we can decide how much power goes to each of these by turning the delay line. So here's a color-coded version of the same thing. This picture does not have the delay line, but here's the light source. The beam splitter here is shown as a partially transmitting mirror. And here's a version of the Mach-Zehnder interferometer where we don't have this beam splitter in place. We just have 50% of the light going this way, 50% of the light goes that way. And each detector will get 50% of the light. If you shine sunlight into this, each detector will be recording 50% of the light. And the first question is, well, what happens if we don't have a bright light source? So we have a so-called feeble light source, one photon at a time. How does a feeble light source propagate through this? And the answer, when there's no beam splitter here, the answer is if we shoot one photon, which is certainly feeble, at this beam splitter, there's a 50-50 chance whether that photon goes this way or this way. If it goes this way on the red path, it will be seen by detector 1. If it happens to go this way, the blue path, it'll be detected by detector 2. And there's no way to know which way the light goes when it gets to this beam splitter. It's a random process. Mother Nature decides which way. And what we'd have in that circumstance, with no beam splitter up at this point right here, occasionally we would hear a click from D1 and then D2 and back and forth. Randomly, we would collect data from both of those. This is a so-called open configuration of the Mach-Zehnder interferometer. And there's discussion here, you can read at your leisure to get more comfort with how this works. Light propagating from BS1 to M1, which is this, to D1, and so forth. So let's take a break. I'm going to get a glass of water. I'll be back at 2:05, and we'll talk about Wheeler's version of this Mach-Zehnder interferometer. Okay, it's 2:05. So let's get back to the Mach-Zehnder interferometer and how you use it to explore the behavior of quantum waves and particles. So Wheeler, as usual, has an inventive way to deal with this interferometer. It's called his delayed choice experiment. Remember, that's virtually the same title we had when we were talking about his version of the double slit experiment, where we delayed choosing the configuration of the experiment until after the photons were already essentially done propagating through the experiment. By the way, here's the way the delay line works. It just adds a path. I mean, there's multiple ways to do it. The one that's most understandable is that we just add a little more path length to the path of one of the waves, kind of like when a trombone player moves this slide. In fact, telescope systems like this one that I worked on in the 1990s have delay lines, and these are what they look like. These trolleys move back and forth just like the slide of a trombone, and they change the path length of light propagating through this multiple telescope system. To give you a sense of scale, the mirror in each one of these telescopes is 8 meters in diameter, about 25 feet or so. And this is a giant and very productive facility down in Chile on a mountaintop down there. So we've already discussed the open configuration of the Mach-Zehnder interferometer. Here it is again, except in this version, I'm showing the delay line. There's someone's hand turning the knob that adds a path delay, and that allows steering the light entering the system to either detector 1 or detector 2 or both. Okay, so we have this delay line. Now let's go to what's called the closed configuration. Here it is. We put this beam splitter back in. So the path length through here encounters a beam splitter here. So some of the light goes to D1 and some goes to D2. And again, if you turn the knob, you can decide how this light is going to be distributed. I said something wrong just a minute ago. In this configuration, changing this path does not change how much light is received, because every bit of light that passes through this beam splitter just hits a series of perfect mirrors, and there's nothing here, so the light goes to detector 2. This path was even simpler because it doesn't have a delay line. All the light that happens to go this way goes to D1. So I apologize for saying that incorrectly. But if we put the second beam splitter, there it is, beam splitter 2, we put that in, then things get interesting because we can turn this knob and control how much energy goes to detector 1 or detector 2 by just how we have aligned these, the red wave or the blue wave. And here's a little illustration of that. By changing this relative position of the red and the blue, we can change the peak and so forth. Now, if we send a quantum into this system, we have a 50% chance here of the light going that way or that way, and the same here. So we're still seeing random arrival of individual photons there. Now, Wheeler's conception is we can delay whether this beam splitter is in the system or not after the photons have encountered beam splitter 1. So imagine in slow motion, really slow motion, a photon enters. We don't know which way it's going to go here. This is just a random choice made by Mother Nature. But when the photon is, perhaps it's here, or perhaps it's over here, we don't know. Is it going to behave like a particle or a wave? And that's determined by whether this beam splitter is in place. If we remove that beam splitter, we have the open configuration illustrated here. And if it happens to go on the red path, it will certainly go to D1. If it goes on the blue path, it will certainly go to D2. And changing this knob doesn't change that because all the mirrors involved are 100% mirrors. But if we decide while the photon is in the system, whether to install this mirror or not, we should get some interesting results. And technology allows us to do this. We have very high-speed electro-optical devices that allow us to randomly choose whether this mirror, this beam splitter, is in the experiment or not. And that choice can be made after the photon has encountered beam splitter 1. So this is a discussion of the results. Indeed, if you look at the data when the beam splitter is not in the system, that is the open configuration, and you turn the knob, the phase shifting knob, it doesn't affect anything. You get the same result. So red and blue here indicate whether we're looking at detector 1 or detector 2. So if you change the phase shift and it's a configuration where the second beam splitter is not there, nothing changes. On the other hand, if you're looking at a situation where the beam splitter is present and you change the phase shift by turning that knob, then you do see fringes. Depends on how much you turn the knob. Some of the light goes to D1, some of it goes to D2, and so forth. So now when I say turn the knob, nobody's doing this by hand. It's all under computer control, and it's done with random choices so that no influence of the human experimenter can confound the results. But what we're seeing very clearly is in the closed configuration, so that beam splitter 2 is in place, we see wave-like behavior. You can only see this happen if waves are interfering. And remember, we're doing this with single photons at a time. So the individual photons, when we're in the closed configuration, the photons are behaving like waves, even though the experiment doesn't start until the photon has passed this beam splitter. So it's embedded in the experiment, not knowing what it's going to encounter here, and it always does the right thing. Now, again, Wheeler's interpretation was he invoked retrocausality and said, oh, it's because somehow the presence or absence of this beam splitter was conveyed to the photon here at its source, and it was emitted as a wave or a particle because it knew it was going to encounter a certain experiment configuration. No, that's not the case, which is good because we want causality in our world experience. We've had to give up causality in, for example, the case of radioactive materials. You can sit and watch a radium atom decompose by ejecting an energetic particle, but the timing of that is completely unknown. It's can't be predicted. All we can talk about is the statistical outcome of experiments of that kind. And we assigned a single number called the half-life to radioactive emission experiments because the individual cases are totally unpredictable. In this case, that applies to this beam splitter. So the right way to interpret this is very similar to the delayed choice double slit experiment, where we run an experiment. Let's say we run 100,000 photons through this, and randomly we decide whether we're going to invoke this beam splitter or not, a decision that is made after the photon encounters this mirror, this half silver mirror, and we keep the data segregated. That is, we know, was the beam splitter present or was it absent? And the result is, for every case where the beam splitter is present and we do our experiments with phase shifting, we see wave-like behavior. And in the case where we have the beam splitter never is not present, then we get these results. So everything makes sense, and quantum mechanics predicts these results. And this is real laboratory data. There's a reference here that you can go look at if you want to see this. Now, an intriguing version of this is to extend Wheeler's delayed choice experiment to space. So let's look at that. And this experiment was done, I don't know, 10 years ago. So we have a light source in space. Beam splitter 1 is in space. And then we have a way to direct the outcome of this beam splitter to a receiver on the ground that is either there or not there, depending on a random choice by a computer. Notice this is a Mach-Zehnder interferometer. It has beam splitters. One way to describe this so that might resonate with sports fans is, if this is home base, there's second base, there's first base, there's third base. First and third base are always perfect mirrors. Second base is put in place or not, depending on the whim of a computer, so that no humans are involved in this. Because humans could not react quick enough to do this. Everything here in the laboratory version of these experiments, the installation or removal of this beam splitter occurs on a scale of nanoseconds. So what does this tell us? First, and one thing I did not emphasize enough, I'm going to emphasize it again. Excuse me for backing up. Let's go back and talk about the issue of which way. Remember, I talked about in the double slit experiment that if you know which way the quantum particle had progressed, you don't see fringes, you don't see interference, superposition, all those things are eliminated. If this mirror is not present, if this beam splitter, is not present, we know which way the light went, because either detector 1 or detector 2 chirped and said, I just caught something. Let's do it more specifically. Here is the open configuration. Remember, this is a random process. Beam splitter 1 produces randomly a path for the light, the photon, going this way or this way. If there's no beam splitter here, we know perfectly well which path was used by the quantum particle, because either D1 or D2 reports getting an electron. That it never happens that the electron appears simultaneously in D1 or D2. There's only a one electron or photon in this system at a time. So I should have emphasized that point, that in the open configuration that is drawn here, we know which way the quantum went. And as soon as you know which way the quantum went, there can be no interference. There can be none of the fringes that we have seen in other experiments. That's what we're seeing here. This shows us we don't know, we know which way the path was, and we don't see any of this fringing. Now, this fringing is different in a sense. You can't take a photo of it because it depends on changing the phase of that delay line. So this has been done in space. And when this beam splitter is in place, we see the interference fringes that are so typical of wave-like behavior, even though the experiment is now measured on a scale of 1,200 kilometers. If we take out this beam splitter, again, that's a random process, then we know which way the photons went. They either went this way to this detector or this way to this detector. So there's no spatial scale limit for demonstrating this kind of behavior, and a very challenging experiment to do. So there's a discussion here of interpretations, and I've said everything that I've written here already in this lecture, that if we know the which way path, we don't see the quantum effects. Now, when I say, now we're going to discuss just very briefly something we'll discuss again next week in more detail, and that is interpretations of what's going on in the delayed choice experiment. This is a new topic for us. We haven't discussed this before. But in the context of quantum mechanics, the idea of interpretation has become a focus of understanding and embracing a philosophy of what's really happening at the level of the quantum and the experiment that it's embedded in. There are many interpretations of quantum mechanics. There's almost no agreement between them. If you compare one to the other, right now, there's probably 10 or 12 that are prominent, that are continue to be argued about. This is not an issue for classical physics. In classical physics, such as Newton's explanation of gravity, which led to an explanation of why the moons of Jupiter orbit the planet the way they do, all that is explained by Newton's law of gravity. And the result is Kepler's laws of motion, which were based on observation, are not needed. You can predict the motion very accurately by using Newton's laws of motion, and interpretation of what's actually happening is not necessary. You can observe, you can make observation of the motion of the moons or the orbit of Jupiter around the sun. The same laws apply. The kinds of arguments that have emerged related to quantum mechanics were unknown in the classical world. They just weren't needed because up until the mid-1800s, everything that was being discussed could be observed. Quantum mechanics is different in that way. If you insist on determining, for example, which way a quantum particle moves through an experiment, your attempt to uncover that fact, as we have discussed throughout this lecture today, you destroy the quantum behavior that you're trying to dig into. So what I just have very briefly, an introduction to a few of the interpretations. Back in the 1920s, Louis de Broglie had this idea that the behavior of quantum particles, or quanta, was determined by an invisible influence that determined the outcome of experiments, the so-called pilot wave. And this paragraph summarizes how you would apply the pilot wave interpretation to explain the Wheeler delayed choice experiment. You see there's reference here to the various parts, the beam splitters and the detectors. A modern interpretation of has reemerged in the early 1950s. David Bohm independently came up with essentially the same thing that Louis de Broglie had in mind in the 1920s. De Broglie was talked out of describing the behavior of the quantum world by this pilot wave concept. David Bohm was more persistent, perhaps, and had more tools at his disposal, and his idea is still in play. Modern books still treat this as a realistic way to interpret what is going on in the quantum world. A more exotic approach is the many worlds interpretation. This is invented by Hugh Everett in the 1950s, and it says that when quantum processes evolve, at each juncture, for example, when you insert or remove the second beam splitter in the delayed choice interferometer, an entire new universe is created. That is, there is branching of the universe in which the experiment was started. And in one of those, the quantum event of the photon or wave encountering the beam splitter suddenly creates a new universe, so that there are two outcomes. One where it acts like a particle, one it acts like a wave, and those universes are no longer accessible to each other. Here's an interpretation of it for Schrodinger's cat. We've talked about this before. There's the cat. There's some kind of radioactive something, a radioactive atom. And if the atom decomposes, then a hammer strikes the poison and cat dies. In Everett's interpretation, there's a split right here. As soon as the radioactive event occurs, that's a quantum event, it splits the universe, and the other path, notice in the other path, there is no smashing of the poison and the cat's happy. And those two universes go their separate ways. That implies the existence of an infinitude of universes in which quantum experiments continue to evolve and be conducted, and all of us are in, or some version of all of us are in all of those universes. If you're in the physics lab and the experiments are underway, according to Everett, you are branching into an infinite number of future universes that are no longer connected. There are other interpretations. One of them, this transactional thing, suggests that there's some backward signaling, reversal in time. There's a wave traveling backward in time, somehow lets the particle or the quanta in question, lets it know what it's about to encounter. This is very similar to Wheeler's ideas. And one of the key issues of all these interpretations is, are they testable? And so far, there's been no experiment that reveals which of the many interpretations of quantum mechanics are worth taking seriously. We also have emergence of this idea of quantum field theory, the modern version of quantum mechanics that has replaced but is complemented by the Schrodinger equation, and that there's an interpretation accessible from quantum field theory that tries to explain what's really going on when beam splitter 2 is put in or taken out. So we'll discuss this a bit more next time, but let's carry on with our explanation of modern experiments. I've already said that there's been a demonstration of wave-particle duality with large complex atoms, molecules. Look at this thing, 284 carbon atoms and so forth. These are called porphyrins, and quantum mechanics describes the behavior of those systems. Indeed, there's a particular different kind of an interferometer. It's similar to the Mach-Zehnder. The difference is because of the mass of the particles involved here, so 810 atoms, the components that are used are not the typical mirrors that I showed you in the description of the Mach-Zehnder or Wheeler interferometer. Rather, they use beams of light that are interfering and use those to direct these more massive objects, still at atomic scale, and they see the interference patterns shown here that are indicative of wave-like behavior. All of this scales to much more massive systems. One way to see the relative mass of these is that if you do these experiments with, say, a hydrogen atom, which has a single proton, and in a hydrogen atom, the proton, the nucleus, is dramatically more massive than the electron. Some of these molecule or molecular experiments have enough atoms that there are 10,000 protons involved. Because remember, if we go look at carbon, for example, it has more than one proton. There's some hydrogen, it has one proton, and so forth. So when you add this up, you end up with tens of thousands of protons, much more massive, and yet we still see quantum effects. Here it's very distinct. This is a carbon buckyball, C70, 70 carbon atoms bound together by their electron behavior in a different kind of interferometer and a different kind of detector. So it's a little more complex to interpret in a physical way. But a molecular beam goes in, you have a standing wave of light that influences the beam similar to the beam splitter that we used in the Wheeler experiment. And we have an ion detector and so forth. And you can see this behavior, which is indicative of wave-like behavior. Here's yet another one where it's some physical motion of a grating. There's multiple gratings here. Same idea. By moving something, you can see interference patterns indicative of wave-like behavior. And if you turn off the gratings, you don't see that. So there's a variety of these very interesting experiments that are done that exhibit, here's polypeptides with 1,800 proton masses demonstrating matter waves, that is, a piece of stuff, a polypeptide behaving like a wave. Now we come to something very intriguing, and this is called nested interferometers. So I've already shown you how Wheeler's delayed choice experiment allows observation of wave-like or particle-like behavior depending on how the experiment's configured, even after the quantum enters the system. This experiment starts with a Mach-Zehnder interferometer. It's geometrically a little different, but there's the light source, there's the two beam splitters, and two perfect mirrors. And this is an intriguing approach that I'm going to describe in more detail in a future version of this chapter. What they do is they stimulate vibrations in mirror A and mirror B, and when they inject light and analyze the light with this device here, a detector that can pick out the frequencies of motion of detector A and B, we see two bumps because they've asked mirror A to oscillate at 285 or so, 282 frequency, for that frequency, and B oscillates at around 295. This detector and the analyzer behind it can pick out those frequencies, and we see that light going in reveals itself in having touched mirror A and mirror B because we get these bumps at those frequencies. Now things get strange. Let's suppose that instead of having this beam splitter, we remove that. So the light that touches A goes off and we never see it again. Look at, does mirror A see any light? It's the same scheme, but we never see any evidence that light has touched mirror A. Mirror B, on the other hand, still says, oh yes, I saw some light. So already this is a little bit mysterious, but there's more. And by the way, the experiment I'm about to describe to you has been around for a while. It started 10 years ago, roughly, and has this intriguing title, Asking Photons Where They Have Been. And then the response in 2018, we do this the same style. The assertion made that the photons are lying about where they've been. But nonetheless, I'm going to show you this. And the debate about this experiment continues. I find it really intriguing. And the way that you do this is, remember, we have a light source and a beam splitter, another beam splitter, and two reflecting mirrors, except we now put another Mach Zehnder interferometer with a delay line inside of this bigger one. So we have nested interferometers. And the upshot is shine a light on beam splitter one, just like we did in the Wheeler delayed choice experiment. Some of that light goes to mirror E, some goes to mirror C. And again, in this case, the light that goes to mirror E goes into this interior beam split interferometer. I've drawn a circle around it, but the output is thrown away. It just goes away. And notice which mirrors reveal that they had been touched by light. Mirror A, right there. So some of this light went this way, hit the beam splitter, encountered a delay line, and went to mirror A, and we see that in the analyzer. Mirror A felt some light. Mirror B here felt some light. Not a surprise because the light from E could go through the beam splitter and hit this mirror. And sure enough, B says, yep, I saw some light. Not as much as A. That's a little bit mysterious since we know this beam splitter splits 50-50. Each photon has a 50-50 chance of going this way or this way. Mirror C also saw light. Again, this beam splitter splits 50% and 50%. But mirror E in this configuration sees nothing. There's mirror E. It's barely a little bump. And mirror F sees nothing. This business of why mirror E, which obviously was doing something because A and B, they are here, could not have been exposed to light unless E put the light there. This remains a mystery. Now, there's another version. Once again, we have two Mach Zehnder interferometers. We have our light source. There's a beam splitter. There's a beam splitter. Again, that's like home plate, second base. Here's first base. Here's third base. And then we have another interferometer. But this time, this beam splitter is present. In the previous version, this didn't exist. Let's see which mirrors are active. A, yes. B, here it is, yes. C, here, yes. Now we put this beam splitter here, and now remember, mirror E in the prior experiment saw nothing. Now there's a huge amount of light banging on E. And mirror F, which also saw nothing in the previous version, as the largest outcome. These results are being debated now as recently as September of this year. 2 months ago, there was yet another paper trying to explain this kind of behavior and why the peaks are the way they are. Notice this peak is here, and that's A, and its partner B, which should see the same amount of light because that's a 50-50 beam splitter, is a little higher. Nobody knows what's going on here. And if we, again, change the configuration a little bit, we see some of the mirrors, namely E and F. In this case, F sees nothing. So these kinds of mysteries are being studied. Oh, and by the way, if we block this path, which we have not tinkered with before, we just 50% of the initial light goes through this beam splitter and hits this mirror, and we put a blockade there, none of the mirrors see anything. This remains mysterious. As I say, there's lots of controversy about this. And here's Einstein talking about the behavior of quantum mechanics. He had many Gedanken experiments he came up with. Of course, he never saw any of the modern ones. The technology did not exist, but he said quantum mechanics is very impressive, but it's not yet the real thing. And here he's referring to God, the old one. So some of this just leaves us paralyzed. We just don't know how. And as I say, I'm going to add some more material. There's another one. This is a very interesting thing I've just gotten interested in. The Hardy paradox uses versions of these complex interferometer setups, but it doesn't use light. It uses electrons and positrons. In fact, it could use any particle and its antiparticle. And what Hardy found 20 or 30 years ago, maybe more, is a paradox that quantum mechanics predicts that if you put electrons and their antiparticle, the positron, into an experiment like the nested interferometers I just showed you, you get two possible outcomes. Either the particles find each other and annihilate, or they don't. And people are trying to conjure up experiments where you can actually do these kinds of experiments to see what really happens. Now, it turns out that photons and electrons are not the only particles or quanta that exhibit these interesting properties. We also have neutron interferometers. And these have to be built in a special way. We have a neutron beam, and the interferometer is made up of this structure, the gray part, which has to be machined out of a single block of material to provide the stability necessary to observe interference in an interferometer like this, because we're dealing with neutrons. And the phase shifter is very simple. It's a block of material, silicon-based material, and if you rotate it, the path length through the material changes. So the shortest path would be for the phase shifter block to be perpendicular to the neutron beam. If you rotate this, the more you rotate it, the longer the path that has to be taken by the neutrons. And indeed, this kind of experiment has been done, and it exhibits phase rotation of the kind we saw in the Wheeler delay choice experiment when the little hand there was turning the delay line knob. That's what's going on here. Of course, nobody does this with their hand. It's done with an electromechanical device that can be moved on a scale of nanometers. But there it is, neutrons behaving like waves if they're exposed to this kind of experiment. And presumably, I don't think this has been done yet, you could do the Wheeler delayed choice experiment with such a device. The problem is you can't move a block of silicon in a matter of nanoseconds while the neutron is progressing through this experiment. You might be able to do it with slow neutrons that are not moving at the speed of light. So I actually don't know. I'm going to make a note to myself to see if anybody has done a neutron delayed choice. And if I find something in the affirmative, it'll become part of this chapter. So again, here's, oh, and this is actually, not to turn, let me show you this. So I'm going to stop sharing. I'm going to show you my desktop because a new window is going to open. So we click here and we'll probably have to watch, nope, no ads. So we're going to start this. This is, you'll recognize, this is the neutron interferometer. Now watch, here comes the neutrons. Notice the size of the delay line. That's actually getting thicker as the experiment progresses. Instead of rotating this, they just make it thicker. So the neutrons have to spend more time in that silicon material. And what do we get out of this? We get evidence of wave-like behavior. We have two detectors. So this is essentially the Wheeler delayed choice experiment, except this beam splitter, sorry, this delay line is in there the whole time, but it's the thickness of it keeps changing. Now, we have about 10 minutes left. Let me ask right now, any questions?
Yes, we have a handful of questions.
Oh, okay.
The first one, are you
ahead.
ready for me? Okay. The first one is, are these thought experiments or actual experiments? And if real, how do they move the slit film fast enough? And if Wheeler's experiments are thought experiments only, how do we know they are accurate?
Okay, so let me make a copy of this. So in case I don't get through the answer today, I will send out a note with the answers. The Gedanken experiments I've showed you today are real experiments. The technology exists to put in or remove the second beam splitter in a matter of nanoseconds. And the delayed choice, you should all be seeing this since you can see my desktop. The slit film, that one, I don't know if that's ever been done. I think people saw Wheeler's idea, but then they got intrigued by the interferometer version of his delayed choice experiment. And that one does exist. So maybe that has not been implemented because people said, oh, it's a double slit experiment. We're more interested in interferometers. Wheeler's, okay, this question, if Wheeler's experiments are thought experiments only, let's just stop there. They aren't. His delayed choice experiment has been conducted in a laboratory, and quantum mechanics predicts the outcome. If the second beam splitter is in, we see wave behavior. If the second beam splitter is not in, we see particle behavior. And so these two questions are connected. Doesn't it mean the experiment influences itself? Okay, I'm going to give that some thought. I'm not quite sure. How do these experiments eliminate interaction of quantum particles with other particles? Yes, there are quantum particles that form in the case of the double slit. Yes, the double slit screen is made of atoms. But the argument is, there's an argument, I'll go into some detail in explaining the answer to this, that the atomic nature of the double slit is suppressed by something called decoherence. That is, the atoms in the screen that holds the two slits are in intimate contact, and any quantum behavior they might exhibit, namely entanglement, that gets destroyed because the neighbors are constantly bumping into each other. Do single photons exist in the natural world? Yes. We wouldn't know about them. I mean, they come from a very feeble light source or a very distant light source. But we're not out there looking for individual photons. We can do it. Astronomers do it all the time. They look at sources that only trigger one event in a photodetector, only because the light source is so far away. But yes, single photons exist in the natural world. Entangled photons, are they separate? Yes, they are separate. And I see there's more to this, but there's something I want to show you before we're done. If so, can't they behave differently as a result of interaction? No, the BBO crystal produces two independent photons that are entangled. Okay, and then Mike asks, is there a different, how photons interact with the mirror? Oh, that's the key, Mike, to the delayed choice experiment. How the photon interacts with the first beam splitter, there's no way to say it. It's a puff of light, or it's a wave that exhibits its nature when we get to the end of the experiment. We can't know how we're calling it a photon. We have to remember it could mean it's a particle or a wave. That's why I like to use the word quantum. When the quantum encounters the mirror, we don't know anything about its nature. We have to ignore that and wait till the experiment is over. And the experiment's only over after we install or remove that second beam splitter. In fact, I'm going to set this aside. I have a copy of it. And we're going to go back to this. I got to get rid of this. Can't seem to get it. Okay. Real quick, we're going to jump to the end here because I want to show you some demonstrations and you'll get a sense of what we're dealing with. There's lots more here that we don't have time to talk about. But what is here, and you can do this yourself, is these are demonstrations provided by the University of St. Andrews in Scotland. And here's a Mach-Zehnder interferometer. It's the same configuration I drew for you. And I'm going to show you, let's turn on the controls. And we have classical particles, and we are going to shoot particles, physical particles like BBs. They're hitting the beam splitter. Sometimes they go this way. Sometimes they go through. So, and you can look at the statistics over here. If you run enough, you'll see it's 50-50. Now let's look at electromagnetic waves. half of the light, fine. Remember, this is an open configuration. There's no beam splitter here. And half of the light is going to detector 1, detector 2. If we jump ahead, you see roughly 50-50 split. And if you did 10,000 or 100,000, you'd see exactly the same power going to each detector. Now let's do it with photons. You're going to see random behavior. We don't know which path the photons took. Let's jump ahead. Notice right here, it's about 50-50 because this beam splitter is the only beam splitter in the experiment, and it is a 50-50 split, whether the photons go this way or that. Now, let's stop this and then put in the other beam splitter. Notice this is the phase shift. My implementation is different. It's nonetheless, this is a phase shift. Now, let's start shooting photons. And I'm going to add some phase shift. And the beam splitter is in there. Now let's jump ahead. Still 50-50. But now, if I change the path length with the beam splitter in, now notice it's not 50-50 anymore. This is wave-like behavior. So more of the light, more of the photons are ending up at detector 1 than detector 2, even though this is guaranteed a 50-50 beam split and this is guaranteed a 50-50 beam split. If I change it a little bit more and fast forward, notice still way out of balance, detector 1, because of the phase shifter, most of it's going to detector 1. If I remove the beams, so you can do this as long as you want. And there's many other experiments here on this page. Every one of these green boxes is a separate experiment. Here's a delayed choice experiment. Again, let's go to the controls. You can continuously fire. Oh, and we want to turn off the delayed choice. Oh, insert the mirrors. So this is Wheeler's delayed choice. It's almost the same as the one we just looked at. All right. Now we're going to put in the second beam splitter. The prior experiment's better because it shows you the statistics. Just watching this, you can see we don't, when it draws it like this means we don't know which path that quantum went. We can block things. So anyway, if you find that amusing, you have all sorts of experiments here. There are many of these, many more than this on the St. Andrews website. These are the ones that pertain to what we're interested in. And here's the famous quantum eraser. The community is trying to get rid of this use of the word eraser. Nothing is getting erased. What's happening is we build a database of results depending on whether beam splitter 1 is in the machine or the interferometer or not, and then look at the data separately. Sequester some of the data which the beam splitter was there or not, and you see the quantum effects either present or absent. But nothing's getting erased. And it's too bad that that kind of terminology came into being. I mean, Wheeler was a genius. A lot of stuff he left behind is confusing to people. But we're at the end. I will take a look at your questions in more detail. And I think one, or at least one of them, I have to draw a picture to explain what's going on. So it's very near 3 o'clock. I thank you for your attendance. I know part of this is now filled with mystery, and we'll try to resolve some of these issues next week when we talk about interpretations of quantum mechanics. But I can promise you now, explanation of why these things happen the way they do defies our intuition and everything we bring to it from our experience in the natural world we visit every day. And that's the intrigue of quantum mechanics. So thank you for attending, and I look forward to seeing you next week for our last lecture.